Hello, welcome back to es346 Basic Thermodynamics. This is Module 3.2, Phase Diagrams. The sections in the textbook are 3.4 and 3.5. So here are the learning outcomes for this module. At the end of this module, you'll be able to construct a 2D phase diagram. You'll be able to find numeric property values on a table, and you'll be able to use quality to describe mixtures. So first, let's go ahead and review a couple of the phase diagrams. In the previous module, we drew a TV phase diagram, and it looks sort of like a hill that way. A couple points to remember. Right up at the very top, that was the critical point. This over on the left-hand side represented saturated liquids. The line over on the right was saturated vapors or gases. Underneath this is where mixtures occur. And on the far left, these are compressed liquids. And up on the upper right up here are superheated vapors. Recall from the state postulate, any two variables, we can go ahead and find all of their properties, and we realize that any value in TV is going to occur somewhere on this diagram. Now here's the PV diagram, and I'll give you a minute to think about what that looks like. It's also sort of this hill-looking device. The critical point is right up at the top. And instead of indicating the regions, because they're similar to what I had before, I'm going to go ahead and draw an isotherm. Go ahead and change pen colors. And think about what an isotherm would look like on this diagram. It begins over here in the superheated region. It is straight across the mixture region and then up very steeply. So this is an isotherm. And again, we see any two variables define the system. Here we're using P and V, and we can go ahead and find any other state space out here. Okay, so there's a review of two-dimensional phase diagrams. We can combine those into what's called a 3D phase diagram or a PVT phase diagram. And I show it here. It's a three-dimensional picture from the textbook. And we have three axes. We have pressure. So let me go back to the red pen. Okay, we have pressure on that axis, volume on this axis, and temperature on this axis. Now, if you were to rotate this and look straight on, so for example, if I was to look straight on from there, I wouldn't be seeing the temperature axis. I would be seeing a PV diagram. I would see pressure upwards and volume that on the x-axis. If I was to look at this diagram looking straight down, I would have a TV diagram. Now, the phase diagram, this is a typical phase diagram, for example, water. Any location that water has, any pressure, volume, temperature is going to occur somewhere on the surface of this diagram. And a good analogy of that, I think, is to think of a globe, where if you are on the globe, any single location is going to be defined by a latitude and a longitude. And in fact, if you gave me the latitude and longitude, I could go ahead and tell you what the elevation you're at. Very similar to the phase diagram where given two variables like pressure and volume, I can tell you what the temperature is. Okay, now engineers don't tend to use diagrams other than qualitatively. When we want numbers, we like to go ahead and get them off of tables. And so you'll be using the property tables a lot in this class. I've reproduced here a section of table A4 from the appendix. And this, if you look at the title, it says saturated water as a function of temperature. So that means it's giving me the values that are on the saturation curve with temperature as an independent variable. So if I draw up my phase diagram for a TV diagram, the values in the table are indicating points on this diagram here. So if I draw up a couple points, for example, I see on the table there's values at 10, 15, 20, etc. This value right here, we could say, for example, 10, 20, 30, etc. Now I look and it tells me P sat. That's the saturation pressure. that's the value of the isobar that travels through there. So I know at 20 degrees, this isobar is at a pressure of 2.34 kPa. Now the next two columns give me the saturated liquid and saturated vapor volumes. So this one here is saturated liquid, which is given the symbol V sub F. And then this value here is of the saturated vapor, which is given the symbol V sub G. So again, looking at the 20 degree line, I see my value of VF is about 0.001, and my value for V sub G is about 57.7. Now here I show another property table. This is table A5, and it's saturated water again, but now it's giving me values as a function of pressure instead of temperature. So recall, the saturation curve is the same, it's just the independent variable is a little bit different. So here I'm given pressure. So now the points that are given on the table correspond to evenly spaced values of the pressure. So for example, this could be, if I look at my table on the left, this might be 4, and then 5, and then 7.5, etc. The next line over is the value of the isotherm that's moving through. So at 5 kilopascals, my isotherm value is 32.87 degrees Celsius. And again, I'm given values of VF and values of V sub G for all of these pairs. So this table gives me information of the value that's on that line. Now it's very similar to table A4, it's just the values are at different locations. Let me go ahead and change my pen color to, let's go ahead and give ourselves blue. If I was to look at values on the previous table, they would just happen to fall at different locations on here because they were at incremental numbers of temperature. So for example, if I look between 4 and 5 kPa, I realize my temperature is 28.96, 32.87. This might be the temperature at, say, 30 degrees Celsius. So you get the same information from either table. You can use either one. Sometimes you'll see it's easier to use the pressure table. Sometimes it will be easier to use the temperature table. Okay, so far we've looked at saturated liquids and vapors, which are things that are on the line itself. Go back to my red pen. So there's my saturation curve, and I've got values of the line on the left and the right, but we haven't talked about how to find values in this mixture region down here. Now recall, when we did our thought problem of taking a saturated liquid and then slowly heating it, at some point we have half liquid and some fraction of vapor up here. So we're not a saturated liquid or a vapor, we're something in between. And we've got a volume that's going to appear somewhere in between. For example, this X that I showed here. We can describe this state of this by a value called the quality, and it's defined as the mass of vapor over the total mass. So looking at my diagram here, if I was to take the mass of just the vapor phase and then divide it by the total mass there, I would have this value of X, and clearly X is always going to be between 0 and 1. The value over here, X, is 0 because it's all liquid, so mass of vapor would be 0. And over here, X would be equal to 1 because all of the mass would be in the vapor phase. And everything in between is going to be some value in here. Now, if I wanted to know the value of the volume, it's going to be a mixture of those two regions. So recall that X is a measure of how far I am from the saturated line over the whole distance. I can go ahead and define X in terms of my volume as my value of V minus V sub F over Vg minus Vf. That's this distance right here divided by that distance right there. And that number will always be between 0 and 1. That's because the total volume can change between the saturated liquid to saturated vapor continuously, although it occurs at the same temperature and pressure all the way across. Okay. Now there's some other properties that are important to know other than temperature, pressure, and volume in thermodynamics. So we'll be looking at them more when we start going into the first law. But first, let me just show you where you can find these values. I'm showing you again table A4, which is saturated water, but now I'm showing the entire table. Previously, we just looked at these values on the left-hand side, if you look, there's values for internal energy, enthalpy, and entropy. U is the symbol for internal energy, H is the symbol for enthalpy, and S is the symbol for entropy. Now, internal energy is a measure of how much kinetic energy is inside the molecule. Enthalpy and entropy we'll look at a little bit later in this course, so don't worry about it too much right now. Okay, now if I want to go ahead and find values of U, H, and S, let me go ahead and draw up a saturation curve like this, of, say, for example, a mixture, find the value of U, it's going to be equal to the value on that line plus some fraction of moving across here. So, for example, if this was at a temperature of, let's say, 20 degrees, and I wanted to know the value of U at that point, I would look across and I realize that UF is 83.91. So that's the value there, 83.91. And then I'm going to add some fraction of X times this 23.18, which is the difference between those two values. Let's go ahead and do an example. Okay, so here's the question. I want to know what is the quality inside the tank. And the tank I show over here, I have a mass of 7 kilograms and a volume of 2 cubic meters, and I'm told what the temperature is. So if I go ahead and calculate what the specific volume is, because that's an intensive variable, I'm going to take the total volume divided by the mass. So I'm going to take 2 and divide it by 7, and that's going to go ahead and give me a value of 0.286. And my units are cubic meters per kilogram, because my volume is cubic meters and mass is in kilograms. Now if I look at this value of V, that's of my average volume inside the tank. If I look at my saturation table at 150, I've reproduced it down here on the bottom. Oops, put that. Reproduced it here at the bottom. I realize that V sub G is simply 0.39. My value is 0.286. So that means I'm somewhere in the mixture region. I might be, for example, right there. So if I want to find out what my quality is, that's going to be V minus VF over VG minus VF. And I'm going to go ahead and put in numbers. The value of V I just calculated, 0.286. And now the other values I pull off the table. So the value of VF is 0.001. The value of VG is 0.392. Minus 0.001, and that's going to go ahead and tell me my quality at 0.73. So 73% of the mass is in the vapor phase. Now we can continue this example and now find out what is the internal energy inside the tank. And recall from the previous slide, X is equal to 0.73. And the value of internal energy is going to be something between this 653 value and my 2563 value. In fact, it's going to be 73% over there. So we can go ahead and rearrange the equation. I'll write it here, where X would be equal to U minus UF over UG minus UF. I'm going to rearrange it to solve for U. U is equal to UF plus X UG minus UF. And now plug in the values that I know. So UF is off the table at 653. Plus 0.73, and now I've got the difference between UG and UF, and actually the table gives it to me in shorthand. That's what UFG is, the distance between those. So I'll just go ahead and multiply that by 1910, and that'll go ahead and give me what my total internal energy is, which is 2047. The units on that are kilojoules per kilogram. You see that right there on the table. So now I need to go back and multiply that by my mass to get my total internal energy.